Hi, I'm Dr. Rebecca Heusler, a principal investigator at Columbia University in New York City. My laboratory investigates cardiometabolic diseases for which obesity and excess food intake are some of the most important risk factors. It's been known for many years that lipids in the distal intestine can suppress food intake by promoting satiation, or a feeling of fullness that brings about the end of a meal. Bile acids are molecules that modulate intestinal lipid metabolism, but their roles in intestinal lipid sensing and satiation have not yet been fully defined. Bile acids are cholesterol catabolites that promote the efficient hydrolysis and absorption of dietary lipids. However, there are dozens of different bile acid species, each with their own physicochemical properties, and they are differentially able to carry out various bile acid functions. In this study, recently published in Gut, we focused on a particular subset of bile acids known as the 12-alpha hydroxylated bile acids, which I will call 12-HBAs. These include cholic and deoxycholic acids, and their synthesis depends on the hepatic enzyme CYP8B1. We and others have found that the levels and the synthesis of 12-HBAs is increased during insulin resistance in humans. In mice, we can directly test the role of 12-HBAs in metabolism by knocking out the enzyme CYP8B1. This eliminates the 12-HBAs while allowing a compensatory increase in the non-12-HBAs, such that there is a difference in the composition but not the total amount of bile acids in the body.
Eliminating 12-HBAs by knocking out cite8b1 caused a 10% decrease in body weight. This was associated with lower adult food intake.
How could eliminating 12-HBAs lower food intake? We've also found that eliminating 12-HBAs in mice slows the metabolism of dietary lipid in the intestine. We hypothesized that this could lower food intake by allowing more lipid to reach the distal intestine, thus triggering the lipid-sensing machinery and the attendant satiation. A key mechanism by which lipids in the distal intestine promote satiation is by slowing the rate of gastric emptying. This causes gastric distension and a feeling of fullness. To examine this pathway in our mice, we measured the rate of gastric emptying.
Here, we evaluated the solid phase gastric emptying based on food residue in the stomach after a meal. We found that eliminating 12-HBAs reduced gastric emptying.
Next, we wanted to determine which lipid-sensing receptor was responding to the altered lipid metabolism in the intestines of our mice. We predicted this to be GPR119, which is a fat receptor that is found specifically on the enteroendocrine cells of the distal intestine in mice. If the excess fat in the distal intestine activates GPR119 on the enteroendocrine cells, it can trigger the release of the hormones GLP-1 and PYY, which are known to slow the gastric emptying rate.
To test the role of GPR119, we generated double knockout mouse of cite8b1 and GPR119. The reduced slow gastric emptying in cite8b1 knockout mouse was completely normalized when GPR119 was deleted. This data shows that fat-sensing receptor GPR119 is required for slow gastric emptying in cite8b1 knockout mouse. Next, we measured food intake over 1 week. Deletion of GPR119 normalized reduced food intake in cite8b1 knockout mouse. Consistent with this, knocking out GPR119 normalized the body weight of cite8b1 knockout mouse. Finally, we evaluated the underlying mechanism of slow gastric emptying in cite8b1 knockout mouse. We found that eliminating 12-HBAs increases the intestinal level of GLP-1 and PYY, two hormones known to slow the gastric emptying rate. On the other hand, blocking both GLP-1 and PYY, both signaling using antagonists, normalize the gastric emptying in cite8b1 knockout mouse.
In this work, we demonstrated that CYP8B1 ablation in mice slows the rate of intestinal lipid hydrolysis, allowing more lipids to reach the distal intestine. There, they activate the distally abundant fat receptor GPR119, triggering the release of GLP-1 and PYY, which slow the rate of gastric emptying and promote satiation. It's tempting to speculate that altering bile acid composition, potentially by inhibiting CYP8B1, could sustain some chronic activation of intestinal lipid sensing pathways for obesity and diabetes treatment.